You just took your second exam through Zoom yesterday, and I was just going to go through the solutions to both of the versions that you had, depending on what time you had come in to take the exam. And so this is a great review for the final, which you have next week on Monday. And so going through this, first question, given the derivative of f of x, f prime of x is equal to x raised to the negative 2/3 times x minus 2, and we're answering the following questions. So where is this increasing and decreasing? Well, we're already given the derivative, and since we're given the derivative, we don't have to find that. All we have to do is figure out what our critical numbers are. And our critical numbers are values which set our derivative equal to 0. So our derivative is equal to 0. Well, that's when x to the negative 2/3 power is equal to 0. And that's when x minus 2 is equal to 0. And so solving for this, we would get that x is equal to 0 and x is equal to 2. So we have two critical numbers here. And actually 0, if we look at it, x to the negative 2/3, that's actually undefined. But I can see that it's actually defined in my original. So put our critical numbers on the number line, and we're going to test values on each side. So if you plug in -1 wherever you see an x in here, let's just talk about this x to the negative 2/3 power. This is the same thing as 1 over x to the 2/3 power, or same thing as 1 over the cubed root of x. And it doesn't matter if you square it outside or inside the radical. Okay. And so notice when we go in here, and if we plug in a negative number, well, cubed root, let's say if x equals -1, that's going to be -1, but then we're going to square that number. So that part is going to be positive. And I want a -1, not a +1. So that first piece is positive. Times the second piece. Well, -1 minus 2 is -3. And so that's negative. This is less than 0. It's decreasing. Choose a number between 0 and 2. If we plug in x equals 1, the first piece is going to be positive. And the second piece, 1 minus 2, is negative. So a positive times a negative, this is less than 0. And so that is also decreasing. And then something greater than 2, so x equals 3. First piece is always positive. And 3 minus 2 is also positive, so this is greater than 0, so this is increasing. And so we can see that it's decreasing from -infinity to 0, 0 to 2, or -infinity to 2, and then increasing from 1 to infinity. So does this have any local extrema? Yeah, well, if we have something that is decreasing to increasing, we're going to have a local min. And this is going to be at x equals 2. So we want to find the second derivative to find our concavity. We can either use the product rule on our first derivative, or we can distribute that x to the negative 2/3 power. Just pause. So let's just distribute that x to the negative 2/3, then we don't have to worry about doing the product rule. So if we distribute x to the negative 2/3 times x, we add our exponents. So negative 2/3 plus 3/3 is 1/3 minus 2x to the negative 1/3. So now we're ready to take the derivative, second derivative. And so bring down our power down front, subtract 1 from our power, we get 1/3 x to the negative 2/3 minus 2 times, bring our power down front, negative 1/3, subtract 1 from our exponent. So negative 1/3 minus 3/3 is a negative 4/3. We can clean it up a little bit if we wanted to. So this is the same thing as 1/3x to the 2/3 power. Here's a negative and a negative. So this is plus 2/3x to the negative 4/3 power. You can set this equal to 0 now. I think it's easier once it's a single fraction. And actually that's a positive 4/3 power when I bring it down. So really our least common denominator of these two fractions is 3x to the 4/3. And so what's missing on this piece to get it up to 4/3 is x to the 2/3 times x to the 2/3. And I'm sorry, this is a 1. Yeah. Did I write something down wrong? I did. No, I didn't. Sorry. I did it using the product rule. So I have some different work in here. Okay, so let's just carry on. So double derivative is x to the 2/3 plus 2 all over 3x to, that's where I'm getting something off different. I have the 5/3 as my common denominator. Sorry, I know where I went wrong. When I distribute this x to the negative 2/3 to my negative 2, this right here, now my thing's frozen. Should have been a negative 2/3. And so when I bring that down, that's a negative 2/3. Subtracting 1, that's a negative 5/3. So this is really a plus 4. This is a negative 5 or positive 5/3. Our LCD is 5. 3x to the 5/3. So this is where we actually had to do 3/3 right here. 3/3 plus 2/3 is 5/3. But x to the 3/3, that's just like x. Plus 2 times 2 is 4. Okay, so now I have the same thing I had done when I had done the product rule. So we're looking at where this is undefined. That's when x is equal to 0. And x plus 4, this is equal to 0 when x plus 4 is 0. And that's when x is negative 4. So we have two values that we're looking at from negative 4, negative infinity to negative 4 to 0, and on. So to plug it into your second derivative, a number in each interval to see if it's true or false. And so if we choose a number to the left of negative 4, so how about x equals negative 5? If we plug it in here, -5 plus 4, that's a negative function. And then if I take a cubed root of a negative, that's negative. And if I raise it to an odd power, that's also negative. So my denominator is also negative. This is greater than 0, so we know that it's concave up. Choose something between -4 and 0. So how about -1? -1 plus 4 in the numerator. That's a negative number, all over a negative number raised to an odd power and a cubed root, that's negative. So this is greater than 0, so it's concave up. And then x equals 0 to the right of that, so 1. The numerator is going to be, oops, go back, slow down. We plug in -1, the numerator is positive, right? So this is less than 0. And plugging in +1, we get 1 plus 4 is positive over positive, which is positive. Okay, so sketching some graph that could work for this. We know that we are increasing. So we know that we're increasing or decreasing from -1, or sorry, 0, negative infinity to 0, and then 0 to 2. But concavity is concave up until we get to -4. So let's just do that. 1, 2, 3, 4. So we have a -4 here. We're concave up. But then at -4, we're going to be concave down, but still decreasing. Kind of concave down until we hit x equals 0, and then we're concave up. And 0 to 2, we're still decreasing, but we're concave up. And then from 2 to infinity, we're going to be increasing, and we're concave up. So we could get something that looked like the following. And then part D or E wanted to know what is some possible equation or a possible equation of this function. Well, we're given the derivative, so we can find what the function is by taking the antiderivative. So really all we're doing is we're taking the antiderivative of f prime of x dx. So let's write it in the form where we had distributed that x to the -2/3 to each piece. And that would give us x to the 1/3 minus 2x to the -2/3 dx. Okay, so antiderivatives. Add 1 to the exponent and divide by the new exponent. So 1/3 plus 3/3 is 4/3. Divide by our new exponent, 4/3 is the same thing as multiplying by 3/4. Minus 2. Add 1 to our exponent, so -2/3 plus 3/3 is a 1/3. And multiply by the reciprocal of that new exponent, which is 3/1. We could have any constant in here, and that would satisfy our equation. So I was okay if you didn't put the constant in there, because that was a possible equation when our constant is 0. So we have 3/4 x to the 4/3 minus 6 x to the 1/3. And you could have added any constant in there and you would have gotten the correct answer too. See if there's any questions over that one before we move on. Okay, so this was the first question if you had taken the later exam part version B, where you're given information about f of x and the derivative and second derivative, and you're supposed to graph it. So first we're given that x, when x is less than -2, we're given the first derivative is greater than 0 and the second derivative is less than 0. So basically we know that it's increasing from -infinity to -2. And the double derivative is less than 0, so we know it's also concave down here. When x is -2, we get that y is 9. So we have a point at -2, 9. We're given that the first derivative is equal to 0. So we know that this is a horizontal tangent line. So it's probably going to be a max or min. And we'll know after we look at the next piece, or just a horizontal tangent line, which we've seen this can happen without being a max or min. We are given that the double derivative there is less than 0. And actually that tells me that it can't be a min because of the second derivative test. So it's concave down there. So basically f double prime of -2 is less than 0. So it's going to be a max. Between -2 and 0, we're given that the first derivative is less than 0, so we're decreasing on -2 to 0. We're given that the second derivative is less than 0, so it's concave down. So increasing, concave down. We're going to have a point at -2, 9. It's decreasing from -2 to 0. It's still concave down, so we're going to have some sort of a max there until we hit 0. Oops, except that's not going to work with my graph because of the next piece. Next piece says that we have a point at 0, 7. It's decreasing there. We already knew that. Increasing, concave down, decreasing, concave down. Once we've hit, this should all be concave down and then change concavity. So this is actually an inflection point. Double derivative is equal to 0. And that's where we found inflection points, right? Was when our second derivative is equal to 0. From 0 to 2, it's still decreasing. And it's concave up now. And then at 2, -23, so 2, -23 is a point. First derivative is 0. Second derivative is concave up. So we have a min at this value. And then we're increasing after that and still concave up because our second derivative is greater than 0. Okay, so we have the graph of what that function could look like, and that was part B of that problem. So increasing. Okay. Okay, so for the final, you definitely need to be able to graph functions, know how to find where a function is increasing, decreasing, concavity, inflection points. We looked at rational functions before, so you should be able to find asymptotes, vertical asymptotes, horizontal asymptotes by looking at the limit as x goes to positive and negative infinity. So this was the second problem on version B, and it says a long strip of a sheet metal 12 inches wide is made into a small trough by turning up two sides at a right angle to the base. The length of the long strip of the sheet metal, or let the length of the long strip of the sheet metal be C inches, where C is some constant. If the trough is to maximize capacity, how much inches should be turned up on each side? So we have this piece of sheet metal. We know that this is 12 inches. We know that this is C inches. And we want to fold this up. So we want to fold it up here and right here. And if we fold these up as a right angle. So basically this height now, when we fold this up, is equal to x. So the height of that trough is x. But this base now, because this whole thing was 12, this base now in here, that is 12 minus 2x. So volume, let me just do base, is 12 minus 2x. We're trying to maximize volume, and volume of this trough is equal to base times height times width or length. Or length times width times height. So this length in here is C times our width, which is the same as this base, which is 12 minus 2x, times our height, which is x. So let's just distribute cx to each term. So cx times 12, this is 12cx, minus cx times 2x is minus 2cx squared. So now we have what we're trying to maximize. So we want to find the first derivative. Derivative of 12cx. Well, c is a constant. So derivative is just going to be of x, it's just that coefficient in front, 12c. Minus the derivative of 2cx squared. So bring down our power down front, we get 4cx. We're looking at when is this equal to 0? I notice I can factor out two terms, or we can factor out two things. They both have a 4c in common, which would leave us with a 3 minus x equals 0. So solving for when this is equal to 0, well, 4c is never 0, but 3 minus x is 0 and x is 3. We need to make sure that's where a max occurs. And we can do that a couple different ways. But if we look at the second derivative test, derivative of a constant is 0. So derivative of 12c is 0 minus the derivative of 4cx is 4c. Well, we're never going to have that length as negative number. So this number is always going to be smaller than 0, which means it's concave down. If we plugged in 3, wherever we see an x into the second derivative, it's still negative 4c. So this is a max. And we want to turn it up. That height of that trough should be 3 inches. And that that is not the max, but that's when the max will occur. So this next one is question 2, version A. So rectangular sheet of a perimeter 27 inches and the dimension of X centimeters by Y centimeters is to be rolled into a cylinder as shown in part A in the figure. What values of X and Y give the largest volume? And so I even give you that the volume of a cylinder is V is equal to, so this is what we're trying to maximize, pi r squared H. Well, we want this in terms of just one variable. And so let y, this be the height. So that's equal to our h value in here. We need to figure out what r is. Well, recall that a circumference of a circle is 2 pi r. But that circumference, that's just this top piece here. And once I put it around, this is just that length of x. So we know x is equal to 2 pi r. So we can solve for r by dividing both sides by 2 pi. And we get r is equal to x over 2 pi. And there's another bit of information we know is that the perimeter is 27 centimeters. And so we know that 27 is equal to twice the length times twice the width. So 2x plus 2y. Well, since our radius is in terms of x, let's solve for y in terms of x for this equation. So we would subtract 2x on both sides and divide by 2. We would get 27 minus 2x divided by 2, which is the same thing as 27 halves minus x. Okay, so let's plug it into our volume function. We have our volume is equal to pi times r. R is x all over 2 pi quantity squared times our height, which is y, but y is also equal to 27 halves minus x. So let's just clean it up a little bit before we take the derivative. So this is pi squaring x over 2 pi. That's going to give me x squared over 4 pi squared. All times 27 halves minus x. Notice that one of our pi's cancels in the denominator with this pi up here in the numerator. So let's go ahead and distribute so we don't have to use the product rule. And when we distribute, we get x squared times 27 in the numerator. So 27x squared all over 4 pi times 2, which is 8 pi. Minus, when I distribute to the next term, I get x squared times x, which is x cubed all over 4 pi. So now we're in the form that we can take the derivative. Just bring our power down front. So that 27 over 8 pi, that's just like a coefficient there. So bring our power down front of 2 and subtract 1 from our power, we get x. Minus, we can think of this as 1 over 4 pi if you want. Bring our power down front, which is 3, subtract 1 for our power, we get an x squared. Notice 2 goes into 8 4 times. And so we get that derivative is equal to 27x over 4 pi. Notice we have a common denominator now, so we can just put this in one numerator, minus 3x squared. So we're looking at when is this equal to 0 and when is it undefined? Well, this is equal to 0 when the numerator equals 0. So we're looking at when is 27x minus 3x squared equal to 0. And notice we can factor, we can pull out a 3x, or we can just pull out a 3. And if we do that, we're left with 9 minus x squared equals 0. Well, this factors as 3 minus x, 3 plus x. We're talking about volume, so it doesn't make sense to have the volume negative. And so x is equal to 3. Something's off. I should be getting, I don't remember getting 3 there. I remember getting 9, so let me just look really quickly. I forgot to bring down my x in here. So it should have been 27x, and I can pull out a 3x. And so if I pull out a 3x, that would give me 9 minus x. So either x is equal to 0, which doesn't make sense, or 9 minus x is equal to 0, where x is equal to 9. So it's gonna, and we need to make sure that that's a max. We can do that by finding the second derivative. We can do that by plugging in numbers to the left and right of 9 to make sure that that's a max. Double derivative, would that be hard to do? Not really. So if we look at the double derivative, and I'm going to keep it in this form when I do it, or let's just keep it like this. You can factor out that 1 over 4 pi if you want. So 27x minus 3x squared. So looking at the derivative of 27x is 27 minus the derivative of 3x squared is 6x. If we plugged in 9, so 27 minus 6 times 9 is 54. This is less than 0, so that makes that concave down, and this is a max. It is asking what are the values of x and y. And so we have the value of x, and we can quickly find the value of y because we know that it's 27 minus x. So y is equal to 27 halves minus 9. Get a common denominator. So y is equal to 27 halves minus 18 halves is equal to 9 halves. And we're in terms of centimeters. So 9 by 9.5 centimeters would give us a maximum volume. Okay, so on your final, you should be able to apply optimization problems, so finding maximum and minimums. And you should be able to do that with applications and not with applications. You should be able to find absolute max, absolute mins. So if you were actually on a closed interval of a continuous function, recall that there was a theorem, the extreme value theorem, that says that there has to be an absolute max or absolute min if that condition holds. So you should be able to apply that too. Okay, so doing problems 3 and 4 together on both tests. First, we're doing version A, and both of these are limits. And both of these limits, I would use L'Hopital's rule. If you go in, first thing you do is substitute, and when we plug in 0, wherever we see an x, we get square root of 1, which is 1, minus 1 is 0, and on the bottom we also get 0. So we get the form 0 over 0, which is an indeterminate form. It's rational, so we can use L'Hopital's rule, which says that limit is going to be the same as if we took the limit as x goes to 0 of the derivative of the numerator all over the derivative of the denominator. Well, the derivative of the denominator is just 1. The derivative of the numerator, let's just do this over here. Let's rewrite it as 1 plus x to the 1/2 power minus 1. So when we take the derivative of that, we need to use the chain rule, bring down our power, 1 plus x, subtract 1 from our power is negative 1/2, times the derivative of the inside. So I know some of you guys are forgetting when you do the chain rule to take the derivative of the inside. So that's going to give me here 1 all over 2 square root of 1 plus x. So when we take that limit, we're just going to go ahead and do direct substitution. We don't really need that 1 in the denominator. And so plugging in 0 here, we get 2 times the square root of 1. So this is just equal to 1/2. The next problem, 5 on that exam, you also need to look at the limit. If you go in here, and this one is the limit as x goes to infinity of x times sine of 16x. The problem is with direct substitution, we get this infinity times infinity. And this is another indeterminate form. It doesn't tell me anything. Actually, I don't get that. Let me just talk about this a little more. As x goes to infinity, 16 over x. So 16 over something that's growing really large, this little piece is going to 0. And sine of 0 is 0. So infinity times 0 is an indeterminate form. So this is where we want to manipulate this so that we can find the limit. And when it's multiplication, try rewriting it as a rational function, and we can do that. And a rational function is when we can use L'Hopital's if it's an indeterminate form. So we can rewrite this x down here, or x here, as 1 over x in the denominator. Invert multiply, that would give me an x in the numerator. And we can write sine of 16 over x. So now as x is going to infinity, that sine of 16 over x, that piece goes to 0. And 1 over infinity also goes to 0. So we have that 0 over 0, an indeterminate form. So now we can use our L'Hopital's. And that's in the form that we can use L'Hopital's. So taking the derivative of the numerator, derivative of sine of 16 over x, derivative of sine, that was positive cosine of the inside, 16 over x, times the derivative of 16 over x. So the derivative of 16 over x, or 16 x to the negative 1 power, is negative 16 x to the negative 2 power. All over derivative of 1 over x, or x to the negative 1 power, is negative x to the negative 2 power. Okay, so let's kind of clean this up a little bit. So I have a negative and a negative. That's a positive. Notice we have an x to the negative 2 power and an x to the negative 2 power, both in the numerator and denominator, strictly multiplication. Those can cancel. And so all we're left with is this cosine of 16 over x. Oops, and this 16 here out front. So now taking the limit as x is going to infinity, this 16 over x piece, that goes to 0. But cosine of 0 is just 1. So this is equal to 16 times 1, or 16. Okay, so these are question number 3 and 4 on version B, I believe. Yeah. So again, go through, plug it in, direct substitution. Cosine of 5 times 0 is cosine of 0, which is 1. So we have 1 minus 1 in the numerator, which is 0 over 0 squared, and the denominator is 0. So we get, again, an indeterminate form, and an indeterminate form that we can use L'Hopital's. So we're looking at L'Hopital's rule. The limit as x goes to 0 of the derivative of the numerator. Derivative of 1 is 0. Derivative of negative cosine of 5x. Well, derivative of cosine is negative sine. So we have this negative and a negative of the inside, 5x, times the derivative of the inside, all over the derivative of x squared, which is 2x. So if we're looking at the limit of 5 sine of 5x all over 2x. So you could have manipulated this to look like sine of ax over ax and then say that that's 1. Or we can use L'Hopital's rule again, because if you plug in 0 in wherever you see an x, sine of 0 is 0, and 2 times 0 is 0, so we get 0 over 0. So I just use L'Hopital's rule again. So derivative of the numerator, derivative of sine of 5x, well, that's cosine of 5x times the derivative of the inside, which is 5, all over the derivative of 2x, which is 2. So we're looking at the limit of 25 cosine of 5x all over 2. Well, cosine of 0 is 1, so we have 25 times 1 all over 2, which is 25 halves. Okay, so number 5 on that first exam, also need to look at the limit. If we go in here and we plug in infinity, wherever we see an x, we get a form of infinity over infinity, which is an indeterminate form. So we got to go back in here and we got to manipulate this. And so one way to deal with this is we can multiply by a fancy 1. And there's a couple different ways you can do that. You can do it, and how I did it was I just multiplied by the conjugate of that in the numerator and the denominator. But we could also multiply by thinking of this as an LCD. So it really depends on how you want to do it. So multiplying this by some fancy 1 to make this a rational function. So let me just do it the other way. Let's multiply by x square root of x, that's an x squared. X squared plus 6x, both in the numerator and the denominator. Well, if we multiply that okay. So this piece in here, this, and sorry, I did it the other way. This has to be 1 over. So that things cancel.
Sorry, Professor. I think there should be a sign between the x and the root of the x squared plus xx.
If I was going to multiply by the conjugate, yeah. But if we don't multiply by the conjugate, which I think we can do that, let's just go through and do how I know it for sure works. So let's just multiply. Yeah, so let's just change that sign in there and let's multiply by the conjugate of that. So let's multiply by the square root of x squared plus 6x plus x, both to the numerator and denominator. And so when we distribute to the numerator, that's a difference of squares. So we can just think of that as squaring the first term, which would just give us what was the radicand, x squared plus 6x, minus squaring the second term, which is an x squared, all over. Now we have a denominator of this, x squared plus 6x plus x. And so notice that we have an x squared minus an x squared, that cancels. And we're just left with 6x all over the square root of x squared plus 6x plus x. And so if we do and plug in infinity in here, now we get this infinity over infinity, another indeterminate form. It's in that form that we can go ahead and use L'Hopitals if we wanted to. It just looks like it's really messy to me because I have to use that chain rule on the bottom. Or we can think of this as dividing. Remember, if we got infinity over infinity, we could divide by that variable to the highest power in the denominator. So we can also think about it that way. So let's just again multiply by this fancy one. I'm gonna just do it right here. And if we multiply that by a fancy one, it's going to be 1 over x, all over 1 over x. And so when we distribute it to the 6x times 1 over x is just giving me 6. When I distribute it to the denominator, I want to put that actually underneath the radical, and I can do that. That's the same thing as x squared over x squared. Because square root of x squared is x. And then when I just distribute the 1 over x to this plus to this x, that just gives me a plus 1. So cleaning it up, I just have 6 in the numerator, the square root. Well, x squared over x squared is just 1, plus 6x over x squared is just plus 6 over x. And then I have a plus 1 outside of the radical. And so as x goes to infinity, this 6 over x goes to 0. And so we're left here with 6 all over the square root of 1 plus 1, which is 6 all over 2, which is equal to 3. So like we've seen in the past, there's multiple ways that you can go and approach some of these problems, and some ways are a little easier than other ways. But if you get that infinity minus infinity, that's an indeterminate form. That's not equal to 0. Or we don't know if it's equal to 0, which it isn't in this case, it's 3. So the next is, and this is on version B, and this is problem number 5. So find dy dx when y is equal to the tangent inverse of the natural log of 5x. So we're going to need to use a chain rule here. If you recall, if y is just equal to the tangent inverse of x, dy dx is equal to 1 all over 1 plus x squared. And so here, taking the derivative, this is equal to 1 all over 1 plus. So of the inner piece though, and our inner piece is the natural log of 5x. So we're going to plug that in wherever we saw an x there. So natural log of 5x, and that quantity is squared, times the derivative of the inside, which is the natural log of 5x. Okay, so rewriting this, we got 1 all over 1 plus the natural log of 5 quantity squared times, well, the derivative of natural log of 5x. Well, derivative of a natural log of something is 1 over that something, so 1 over 5x. We got to apply that chain rule. So derivative of 5x is times 5. So notice the 5's cancel, and we get dy dx is equal to 1 all over, I can pull that x out front, x times the quantity 1 plus the natural log of 5. That 5 is, natural log of 5 is quantity squared. Only difference between that one and the test version A was this was still a tangent. It was y is equal to tangent inverse of the square root of 5x. So using our formula, and we can always use triangles to manipulate this, but if we used our formula, then we get dy dx is equal to 1 all over 1 plus root 5x quantity squared times the derivative of the square root of 5x. We'll bring our power down front of 1/2 of the inside 5x, subtract 1 from our power, negative 1/2, times the derivative of the inside, which is 5. So cleaning it up a little bit, we have really a 5/2 here. And here we have the square root of 5x in the denominator, all times this 1 plus square root of 5x quantity squared is just 5x.
Sorry, Professor, is that like 5x?
Oops, it's 5, but the derivative in the inside is just 5, right?
No, I mean the one you have solved above, the one that has ln 5x.
This one?
Yes.
Is that just 5x? No.
I mean, that's only ln 5 or ln 5x.
Oh. Did I miss the x in there? I did miss the x in there. I see what you're saying. Thanks, Mohammed. Right here, this 5, I dropped my x. Dropped my x. You're right. Thank you for catching that. Everything else looked good.
Isn't the derivative of the inside of 10 to the negative 1, inverse 10, isn't that going to be 5 over 2 square root of 5x?
I do have that piece right here. But the derivative of just tangent x? Or are you saying the derivative?
Oh no, never mind. Okay, I see it now.
Okay.
Because you were saying the derivative of the inside was 5.
Yeah, but I was looking at the derivative of the inside of this 5x is just 5. Just that piece was what I was talking about. Okay, so this is number 6, version A, test 2. You're given if x times y squared equals 4 and dx dt equals -3, then what is dy dt when x is 4 and y is equal to 1? And so we need to use implicit differentiation, but both x and y are functions of t. When I look at the first piece, I'm going to need to use the product rule. So if I look at the derivative of the first, that's 1, but you have to write that dx dt here. A couple of the ones that I've been grading so far, you guys have forgotten that. So y times y squared plus the first, which is x, times the derivative of y squared. Well, derivative of y squared is 2y dy dx, or dt. This is equal to the derivative of 4, which is 0. So we can go ahead right now and plug things in, or we can solve for dy dt, isolating that. This case, on this problem, it wasn't too bad to do that. We could subtract both sides, this y squared dx dt. I subtracted that on both sides and then divide by what's in front of my dy dt. So divide by x times 2y. And now just go back in and substitute in what we're given. So this is equal to negative, y is 1, so 1 squared times dx dt, which is -3, all over x, which is 4, times 2 times y, which is 1. So 1 squared is 1 times -3 and times that negative, that's just going to give me 3 all over 4 times 2, which is 8. For it on version B, though, it was a quotient instead of a product. And we're given that the example or the problem that was x plus y in the numerator all over x minus y in the denominator, all times are equal to x squared plus y squared. We're given in this case that dx dt, this is equal to 12. We're given dy dt. This is when x is equal to 1, or we want to find this. When x equals 1 and y equals 0. So I used the quotient rule when I was taking the derivative of both sides, but talking to a student earlier this morning, they had multiplied both sides by that denominator, which actually made their life a lot easier. So we could do that if we wanted to. We could clear our fraction, right? We could multiply both sides by this x minus y. So if I do that, I get x plus y on the left-hand side is equal to, let's FOIL that out. So x squared plus y squared times x minus y, that's going to give me an x cubed plus a xy squared minus a x squared y squared, or x, I don't know if this actually is easier now, x squared y minus a y cubed. So differentiating both sides, derivative of x, that is 1, but it was x is in terms of t, so dx dt, plus the derivative of y, that's 1 dy dt, equals the derivative of x cubed, which is 3x squared dx dt. Plus, I need product rule. So derivative of the first is 1 dx dt times y squared plus x times the derivative of y squared, which is 2y dy dt, minus, I got to use the chain rule again. So derivative of negative x squared is negative 2x dx dt y. Derivative, so minus x squared times the derivative of y, which is 1 dy dt, minus 3y squared dy dt, derivative of y cubed. We want to find dy dt. I can isolate it, but this might be the time where just going in and substituting in everything now might be better. And so dx dt here is 12 plus 1 times dy dt, which we're trying to find, is equal to 3 times x, which we're given 1 squared, dx dt, which we're given it to be 12, plus dx dt, which is 12, y squared, so 0 squared, plus x, which is 1 times 2 times 0. I really don't care about the rest because that piece is going to be 0. Minus 2 times 1 times 12, but then times 0, minus 1 squared dy dt, minus 3 times 0 squared, so minus 0, just because we're running out of time. We're already out of time. So we got 12 plus dy dt equals 36. That's 0. Minus dy dt. So if I add dy dt on both sides and I subtract 12 on both sides, so I get 2 dy dt is equal to 24. It's pausing. And so we divide both sides by 2, we get dy dt is equal to 12. So let me just see what the question is, and then we'll stop there. Oh no. So my computer's freezing. So I have to get out of here. So the only way I can stop this is by exiting this program and coming back in. So I will maybe. Let me just stop the recording.